Next speaker is James Kegere, who's from the chemistry department of United Arab Emirates University at Al Ain. He's going to talk about synthesis of modified titania metal organic framework for CO2 conversion. Go ahead, James.
Good morning, everyone. Thank you so much for the opportunity to discuss part of my PhD research, that is modification of titania metal organic frameworks for CO2 conversion. The background of my work here is on the fact that we are using retinal materials with a vision of transforming so many catalytic reactions. But there are some hiccups that we've had in the past or that still face this field. First of all, these materials work in harsh environments. They should be stable and recyclable. They should also, in the end, make economic sense because we invest a lot in producing them. So one of the challenges that this field faces is the linker stability. This linker stability issue plagued the COFs to the extent that a group led by Yagi were able to work on the conversion of the imine linkages in COFs and convert them into amide bonds, so in a bid to improve the rigidity and performance of COFs. Following through or copying from this work, we decided to apply this methodology to metal organic frameworks by choosing MOF 901, which is a MOF that combines COF and MOF chemistry, through converting the imine linkages in this MOF into amide bonds. We used oxone as the oxidizing agent, and after that, we were able to test the performance of these two materials for cycloaddition of CO2 onto different epoxides. Of course, starting with the synthesis, we were able to successfully make 901 metal organic framework that agrees with both the simulated data and also the published data in literature. And when we did the oxidation using oxone, we were able also to maintain the crystallinity of the structure of the MOF, and also there was just a slight shift to the right for the oxidized MOF that we named MOF 997. And that one showed that we did not disrupt the integrity of the MOF. It also was evident in the thermal behavior. The two MOFs were similar. They were able to maintain their stability until at least 300 degrees. That's where the degradation started occurring. As you can see, for us to be able to prove that we had oxidized or successfully converted imine into amide bonds, we had to first do the FTIR characterization. As you can see clearly, we have a shift in the bonds, shift in the peak region for the imines at 1626 to about 1640, which shows a shift from imine to amide. And then for us to be able to know whether this is complete oxidation and conversion, we had to do solid state NMR. And as you can see, we were able to completely shift the structure of the imine from the region of 160 parts per million to the region of the amide. And also we were able to see the carbonyl-carbon formation and complete disappearance for the characteristics of the imine bonds. Then we followed through with the sorption behavior. We saw that the two materials actually had comparable. Both of them had the type 2 isotherm behavior. The pore distribution were more or less the same, except that MOF 997 showed a little bit of slightly higher pore diameter, and also MOF 997 actually was amazing in CO2 sorption behavior, and the sorption was 3 times more than that of the pristine MOF 901. And we could also verify this with the SEM morphological analysis. We saw that they are actually the same. We did not interrupt with the structure of the MOF. And also we could observe an increase in the percentage of oxygen for the new MOF 997. So using the simulated and also the experimental analysis, we were able to obtain the band gap of around between 2 to 2.5, which is characteristic of the same, at least the reported MOF 901 in literature. And we were able to see the semiconducting behavior of these MOFs that is suitable for photocatalytic applications. So when we applied the MOFs to the circulation of CO2 into CO2 to the epoxides, we were able to obtain quantitative yields for the MOF 997 and slightly lower for the MOF 901, therefore showing us that the new MOF material that we had generated was far better, in terms of photocatalytic behavior, and also could maintain this performance over a number of cycles. And when we applied it to other epoxides, we were able to obtain relatively lower but still the same trend. And we had also to do the linker monomers and obtained a similar trend for the amide bonds, for the amide monomers, which outperformed the TIA oxoclusters and the amine linkers. So the mechanism is simply the MOF being able to open up the epoxide, activating the epoxide, so that it is able, there is a nucleophilic attack by the bromine from the co-catalyst, and then this opening enables CO2 integration and then ring closure, leading to the the regeneration of the MOF. So in conclusion, we're able to achieve complete oxidation, conversion of imines into amide bonds, and also this implication is that we can apply this same technique to very many other types of MOFs without altering the structures, and also we can do other applications for the same. This work would not have been possible without the support of the UAE University, the leadership and the visionary guidance of Professor Yasir Greish, Dr. Lakha Nguyen of UC Berkeley for establishment of the project, Dr. Sheikha, and the rest of the team. I thank you all for the kind attention.
Thank you, James, for finishing in time. We have time for some few questions. Okay, I don't see any question. This thing. Okay, thank you, James, again.